talk about the Obukhov length. Obukhov is actually the last name of a Russian scientist or physicist. Okay, he basically is one of the fathers for developing the boundary layer meteorology. So, what is the Obukhov length? If you remember what I have just given you, the revision here, our understanding is that in a general condition during the daytime, we have a mixed layer, right? So the properties here are rather uniform. And then we have the surface layer where we should have larger vertical wind shear, and then we should have the turbulence generated by shear more. And for this layer, we should have turbulence generated by buoyancy more. So our basic understanding is that in the lower layer of the boundary layer, in the lower portion of the boundary layer, shear should dominate, right? And then there is another part where we have buoyancy dominating the turbulence generation. In other words, the TKE generation, okay? So what is the extent where there is a layer of shear dominated turbulence, okay? So we want to know the extent of this so that we know which layer is buoyancy dominated and then which layer is shear dominated. Okay, so this is the physical meaning of Obukhov length. So how do we do that? We start with the TKE budget equation here. We have the whole equation here. So this is the change of the TKE itself. E is the combined kinetic energy in all three dimensions, and we have the average here. So this is the local change of TKE. So if we have positive terms on the right, it means that this one is increasing in time. If we have negative terms, then we'll have this destruction of TKE over time. Okay, remember that TKE is not conserved. So we need to study the processes happening with different terms here so that we know where the turbulence is generated through which processes here. But the main focus in this lecture are these two terms, okay? Because for this term, it's just affection of TKE by the turbulence itself. So you're just moving the TKE around with the vertical turbulent motion, right? Or the divergence of it. Okay, so this is like the TKE affected by the turbulence itself. And then this one, we have talked about this because P prime is very small and it's very, very hard to measure. So we try to avoid studying this term. We assume that this term is less important comparing to these two. And then we have the destruction or dissipation of TKE through the molecular vibrations, okay? So in this lecture, the main focus will be on these two terms, the buoyant production and loss, and then the mechanical shear production. So bear in mind that for this one, we only have production, which means that for this whole term, including this negative sign here, it's always positive. Whenever we have shear, we have turbulence generated or TKE generated. And here we could have TKE produced or TKE lost due to this term, depending on the stability condition. So if you have a very unstable condition, then this term, of course, is positive, right? If you have a very, very stable condition, then you have a negative term, then your stable condition will help the destruction of TKE. Okay, so this one could be positive or negative. Okay, so you already, I think you remember this heat flux term, and then you also remember this. So it's the vertical affection of the horizontal momentum, right? And Then we turn this into the surface version. So I add the subscript S here. It represents the meaning surface. Okay, so this whole equation is for the surface. Okay, and we need to normalize the whole equation by the surface properties expressed with friction velocity. So what is friction velocity? Friction velocity is actually coming from the profile of the vertical affection of the turbulence of the horizontal momentum. So you have the turbulent horizontal momentum, then it's moved by the turbulence itself. Okay, and then we extrapolate this all the way to the surface, and this one could represent the strength of your whole profile. Okay, if this one is larger, then it means that your profile is moving to a larger magnitude, right? So we also have an absolute sign here, so it's just representing the strength of your flux term. Okay, so the next step would be to multiply. So I have put up the TKE equation here. The next step would be to multiply the whole equation by this term. So I have just talked about this, the friction velocity U star or U asterisk square, and this is U asterisk to the power 3. And then K is the von Karman constant. We have talked about this in the last section, the revision. It's coming to the reference value for K would be coming from measurements. So if you need to do parameterization for PBL, you need to do your own measurements if you want to have the right simulations. Okay, and we multiply the whole equation by this term. Why do we do that? Because this one represents, okay, this term, actually, I have talked about this, it represents the strength of the shear production term, actually. Okay, and then K is put there by conventions, actually. You don't need to, because if you multiply the whole term with a constant, then it doesn't mean anything, but they still put that in here by convention. You'll see why. Okay, and then C is the height, because we are studying the surface layer. We suppose that the flux is constant, and then we can multiply with the height to see the change over height. Okay, why do we multiply the TKE budget equation with this? Because if you have done the multiplication, you can see it here. We have get rid of the unit of the whole term by multiplying. This is dimensionless, the von Karman constant, so it doesn't matter. By multiplying z, so we are getting rid of the unit of the partial z here, and then we multiply the U asterisk to the power 3. We multiply the unit of these three momentum terms. Okay, which means that this whole term now is dimensionless. Okay, which also means that this term is dimensionless. Okay, so this is the simple process of what I have just described. We have the TKE budget equation here, the buoyancy production and loss, the mechanical shear production, and then the dissipation. And we multiply the whole term by this. Okay, and what we get is these three terms. But actually, we don't care about the mechanical shear production, the normalized mechanical shear production. We care about the normalized buoyant production and loss, because now the whole equation is normalized by the shear production itself. We are not dividing the whole equation by this term. We are normalizing the whole equation by this, the surface property. Okay, but still it means the strength of the mechanical shear. So this one it's still representing the strength of the mechanical shear by the U asterisk here. Okay, so now we have a whole new term for the third term in here. If we rephrase the whole term, we'll see that it's also dimensionless, right? Because we make, if you look at this term, it's easier to understand. It's dimensionless, and this term is also dimensionless. And then we rephrase or rewrite all the terms in this term 3, the dimensionless version of this. We write this except for the z here. We write the whole term with the variable L in here. This is the Obukhov length, and Z over L is the Obukhov stability parameter. Okay, it has its physical meaning. You can see that because we have a U asterisk in here, it represents the shear production strength. And on top, of course, it's the third term, so it represents the buoyant production and loss. So it means that it's a ratio between the buoyancy term and the shear term in terms of the TKE generation. Okay. So what is the physical meaning of this L? If we rewrite the green part in here and then put it on the other side, so we have the expression, the mathematical expression for the Obukhov length. The physical meaning is that if we are comparing the strength of the shear production and the buoyant production and loss. So for this Obukhov stability parameter, if we have this parameter less than 0, it means that it's an unstable condition due to positive buoyant production. Why is this negative? Because we have multiply a negative sign in here. Okay, so if it's less than 0, then it's positive TKE generation. All of these is actually by convention. So if you're smart enough, you can develop your own convention. But now, if you want to study convention in this field, you have to go through all this. This is like the standard of what people talked about. You can even see Obukhov length in some of the atmospheric models. Okay, so this Obukhov stability parameter, if it's less than 0, then it's unstable. So it's basically due to the sign of the heat flux in here. And then if it's larger than 0, then it's stable because it's the whole term would be, if this whole term is positive, it means that you have negative buoyant production or buoyant loss. Okay, so the sign is reversed. Be careful here. And the Obukhov length is the comparison where you have the shear dominating layer on the bottom, and then you have the buoyant production layer on top. We want to study how far this shear dominated layer goes. So L is representing how much is going into the atmosphere. So L is proportional to the height where the buoyant factor first dominates. So the buoyant factor maybe it's weaker near the surface layer, but it's getting stronger and stronger, and then in the next layer is the strongest. So we're studying the comparing the contribution between the two processes here. Okay, in the book, this is not the orientation of the graph, so we can see that in here, the numbers here are tilted by 90 degrees. So in here, on this side, we have, it's negative, but we have TKE generation. on this side is positive, so we have TKE loss or destruction. So it's due to the fact that we have multiplied the negative sign in here. So and then on this side, this axis is the height. Of course, it's the normalized height, or you can think of this as the Obukhov stability parameter in here. So it's also dimensionless. So you don't need to know the actual height. When you do measurement, of course, you can normalize your measurements and then put in a graph like this, and then you can see the Obukhov length. Okay, or you can see the exchange, the changing dominance between the buoyant factor and then the shear production term. Okay, in here you can see that for the shear production term, its importance is decreasing with height. So the shear, maybe it's weaker in the higher layer and it's stronger at the bottom, right? And then here the buoyant production is getting stronger when it's going higher up into the atmosphere. And then this is the place where they have similar contribution to the TKE generation, right? This place. So it's not exactly L. L is here. This is the height for L. Z equals to L. And then this one is for the convective situations, when Z equals to half of the Obukhov length, the third and the fourth term have approximately equal values. So they have equal importance in generating TKE when it's half of the Obukhov length. So the Obukhov length is not exactly where they have the same contribution, where the buoyant production is taking over the shear production. It just means that L is proportional to this kind of profile. Okay, so when Z is much less than L, it means that you are in the layer where this red line is much larger than the blue line here, because the shear production is much more important than the buoyant production. Okay, and when you're higher up, when Z is much larger than the Obukhov length, then I'm not talking about this part, I'm talking about much higher up. Then this blue line should be much larger than this red line here, which means that the buoyant production is much more important than shear production when Z is much larger than L, when you're much higher up. Okay, because you are inside the mixed layer. Then in the mixed layer, you don't have a large vertical wind shear, right? So shear is having less influence higher up comparing to the blue line here. And this is, of course, this is the ground when Z equals to 0. Okay, so here I'm showing you different scenarios. So if you have a higher or larger Obukhov length, then your profile extends like this. And this is around half of the L, where they are having the same contribution to the TKE generation. Okay, and when you have smaller L, it means that for most of the atmosphere, your buoyant production or loss is dominating. Shear influence is very small because this layer is not as thick as this layer. So the shear doesn't have a lot of influence in the turbulence generation. Okay, and then when L is it has a value, is a very, very large value. What does that mean? It means that these two profiles, they never meet, which means that it's a neutral condition because they it's a neutral condition. It's by definition, actually. Okay. So the sign of L, I'm just showing you um, the negative Obukhov stability parameter here. If it's positive, then it's loss. It's on the loss side. Okay, I'm just showing the negative side where you have TKE gain on these three graphs. So when you have positive, it means that it's statically stable, because if you're over this side, then your buoyant term would be a buoyant loss term instead of buoyant production term on this side. And when it's on this side, then the two never meet, which is this situation. Okay, it could be stable, it could be neutral for this one. Okay, here is the measurements. So you are seeing, why do you see a range of measurements here? Because the uncertainty of the measurements is large, first of all, and then this for this case here, it could mean that it could be, for this time of the day, it could be a very small Obukhov length, or it could be very large. It depends on the stability condition, I believe. So if you start the story with the sunrise here around 6 o'clock in the morning, then you can see the Obukhov length start to increase. And we are very certain about this because the uncertainty here is small. The Obukhov length increased. What does that mean? It means that you're going from a very large Obukhov value to a smaller one, which means that your buoyancy is taking control, right? If you're going from this situation to this situation, which means that your shear contribution is smaller and smaller if your Obukhov length is getting from here to here. So most of the atmosphere is dominated by the buoyant production. Okay, this is the meaning of that. Okay, and then in the afternoon, it's also could be a small Obukhov length, which means that it could be unstable, but it also could be a neutral situation during the daytime, because your Obukhov length is getting larger and larger. Okay, if it's very, very large, it means that it reaches this state, which is, by definition, it means stable, which is where you have here. I put a neutral here so that you can understand the meaning of this. Okay, and it depends on the stability condition at that time. Okay, and then after that, after the sunset, what happened? Because you don't have the thermals appearing anymore, you start to have the radiative cooling in the surface. Then if you will start with a larger and positive Obukhov length at the beginning after the sun sets, and then it would decrease after sunset. Okay, what does that mean? It means that your Obukhov length is getting smaller, and it's getting smaller, but you are on the positive side, which means that you are having TKE loss, right? And you are moving from the neutral state to a more stable condition for the atmosphere, which means that your buoyant, once again, your buoyant loss is dominating the atmosphere. It's not appropriate to use these two graphs because this is actually buoyant production, also buoyant production. Okay, if your blue line here is on the other side of the graph, then it means it's a buoyant loss condition. Okay, and then after that, after a while, late in the morning time at night, Then you have a range of uncertainty. It could be stable, it could be neutral. It depends on the situation at nighttime. Okay, now you know why we have the different signs here. Obviously, this side, the top of this graph is for the nighttime situation, and then the bottom of this is for the daytime condition. And for the range near zero here, it means that the buoyant factor are more important than the mechanical shear production, because in this zone, in this region, the Obukhov length is small, which is this situation here. So the buoyant production or loss is taking control over most of the layers in the PBL. Okay. Here is the graphical interpretation of the Obukhov length here, and the surface property U asterisk, which is the friction velocity. So if you look at the numbers here, these are representing the heat flux. So the heat flux is increasing like this. So they have larger numbers on this side and smaller number on this side. So if we just focus on one line here, which is representing just one value for the heat flux, but you can see that when the U star, which is representing the situation for the shear production, increase, right? If you're going this way, then it's increasing. So if you're going along this line, the U asterisk is increasing. The shear influence is increasing, then the Obukhov length is increasing, right? You're going from here to here. So your layer where shear is taking control is thicker and thicker. Okay, this is the meaning of this if you go this way. And if you put a dashed line over here and keep the U asterisk the same, what would happen? Okay, if you have the same shear influence, the same asterisk, then the higher heat flux reduces L. So if you go this way, then you're going towards the higher heat flux numbers, right? Because these numbers are higher than these. If you go this way from 12, 24, 48, 120, then what happened? Your Obukhov length is reducing, is decreasing, which means that if your heat flux is increasing, then your shear influence is decreasing. L is decreasing, then you're here, right? This situation, the shear influence is reducing. This is the meaning of this if you go this direction. Okay, I need to give you a very brief comparison between the molecular exchange of motion or heat and the turbulent exchange. Okay, you can see that from a table like this. This is not in scale actually. For this part is the thickest part, and then the shaded part is the surface layer. You can see that the surface layer here is called Prandtl layer, and it's the definition of this Prandtl layer is that we have constant flux with height. But inside this layer, we have a very, very thin layer where friction is very important. We call this the viscous sublayer, 0.01 meter. And then the turbulent influence is decreasing, and then the molecular exchange influence is increasing. So there's a zone in between. So I'm putting a graph here to remind you the molecular transfer by the random motions of the molecules. Okay, it only happens in a very thin layer near the surface. Okay, so we have to do like an adjustment. So this is what I mean. So this is height, and then the turbulence influence, this is the heat flux. So the turbulence is responsible to do the heat flux, but its influence is decreasing when it's very, very close to the surface, within 1 centimeter here. But the molecular influence is increasing, right? It's the highest near when it's very, very close to the surface. But bear in mind that if we add the influence of both of these processes together, we have what we call the effective turbulent flux, which is this thick line here. We can still assume that the flux is constant over height, because if we add the influence of the two of them, then it wouldn't change a lot, the value. We wouldn't change the value a lot here. So in other words, we don't actually have to care about the molecular exchange. So within the thin layer, the molecular transport could be described by this. Again, this is the down gradient approach. If we have a gradient in temperature, then the heat is flowing to the lower end of the gradient of the temperature here. And then we have a constant controlling this kind of down gradient flow of heat in this case. And we have the scale analysis here, the change of the temperature over change of height. Then we have a number here. And then we know the thickness of this. So we know that it's 10 degrees Celsius within 1 millimeter. So that's why when you're standing on a beach, you can feel the great temperature gradient near under your feet, but you don't feel that for your whole body. That's because of this. So throughout the whole course, the surface turbulence flux is actually the surface effective flux. So we have included the influence of both of these with the flux, the turbulence flux. So we can ignore the molecular processes in equations like this. So we have included both of the processes when we are talking about the covariance terms or the flux terms. Okay, so don't worry about this. Okay, this is like a revision for the last lecture. We have talked about the scale analysis. How do we know that this is constant flux with height? Okay, so we know that this is constant with height for the surface layer only, okay, for the Prandtl layer only. So the next question is to parameterize this in the surface layer. We haven't done that. We have done the parameterization for the whole PBL with the K-theory, right? But we haven't done that for the surface layer, and then we also need to do that for the interface between the air and the land surface. Okay, which means that we need to do the parameterization for the flux terms for this whole layer, and also for the interface in the bottommost layer of this surface layer. Okay,